This is the second lecture for Text Unit 5. In this lecture, we relate heat, which we looked at in the last lecture, to chemical reactions and chemical changes. CH4 is natural gas. It's used to heat ovens and stovetops in homes. And where that heat comes from is its combustion or reaction with oxygen. And here we have a balanced equation for that reaction. And sometimes with this balanced equation, you will see this symbol, particularly when you're talking about how much heat you can get from burning natural gas. Here we see a delta. You learned last time the delta often means change. This is a delta H. This actually means change in enthalpy, and that is something you will study more formally later. For our purposes at this point, delta H just means heat. Rxn is an abbreviation for the reaction. And this particular heat of reaction is negative 890.4 kilojoules. Now when this information is all presented together like this, balanced equation with the heat of reaction, this means that 890.4 kilojoule of heat are released when 1 mole of CH4 reacts with 2 moles of O2 to make a mole of CO2 and 2 moles of H2O. Now note again, heat is released. As this reaction takes place, heat comes off. In a sense, what you could think of is internal energy we talked about inside these molecules is released as heat when they rearrange to these molecules. From our point of view, this has particular consequences for thinking about this balanced equation. We can, instead of relating moles of substance to moles of substance, now relate moles of substance to heat. 1 mole of CH4 is equivalent to 890.4 kilojoules. 2 moles of O2 is equivalent to negative 890.4 kilojoules, etc. The relation on the previous slide makes unit conversions between moles and heat possible for a process. So consider this practical question. Suppose that you are using natural gas to make electricity, which has happened in some places and sometimes. You could ask how much natural gas is needed to burn a 100-watt light bulb for 12 hours. Alright, now to answer a question like that, for you to do it, you need to know a few things from me. For a watt is a joule per second, so a 100-watt light bulb burns through 100 joules per second. We're going to let it go for 12 hours. I can use a process of unit conversions to convert that to second. 60 minutes multiplied by 60 minutes over 1 hour, cancel hours, multiplied by 60 seconds over 1 minute, and we've converted to seconds. Then I multiply joules per second times number of seconds the light's on, and I would get the number of joules, 4.32 times 10 to the 7 joules, or 4,320 kilojoules. That's how much heat, that's how much energy the light bulb uses if you leave it on for 12 hours. So turn the light off. Right, the rest you could do. You know that you need this many joules to get released by the reaction to power the light bulb. Alright, the release means we're thinking about negative 4,320 kilojoules. How much CH4 relates to negative 4,320 kilojoules? You can do this referring back to the equation with the heat of reaction information. Attempt that before moving on. All right. Burning 1 mole release of CH4 releases, I have the negative sign here, again, because of releases, 890.4 kilojoules. The negative signs, it's important to keep track of the negative signs, as you'll see here. We start with the amount of energy, negative 4,320 kilojoules. Multiply by a conversion factor to convert from kilojoules to moles of CH4. This cancels kilojoules, leaves us moles of CH4. Now, we can multiply that by a conversion factor you've seen many times. 16.043 grams of CH4 over 1 mole of CH4. In other words, this is just a conversion factor from moles to grams. Moles of CH4 cancel. We have molar mass of CH4 in the numerator in grams. The units left in our calculation are grams. The answer is 77.8 grams of CH4. I thought I would provide you an example of a simple endothermic reaction. This is, of course, not technically a reaction because no new substances are made. We start with solid water and we go to liquid water. In other words, this is about melting a mole of ice. Okay. Heat for melting a mole of ice is 6.01 kilojoules. Positive. Note the sign. Put heat in to the ice to melt it. You can ask questions. How much heat to melt 3.0 moles of ice? Or how much heat to melt 1,000 grams of ice? And you should be able to calculate those heat requirements. Go ahead and try that. The solutions are on the next slide of the presentation. How much heat to melt 3 moles of ice is a straightforward calculation. We have 3 moles of substance. All the coefficients in the balanced equation for melting on the previous slide are 1. So 3.0 moles. 1 mole of water relates to 1 mole to 6.01 kilojoules. So we have 6.01 kilojoules for every mole. The answer is 18 kilojoules. If we have 1,000 grams of ice, we take 1,000 grams, first multiply by conversion factor to convert from grams to moles. 1 mole over 18.0152 grams. Grams cancel, we're left with moles of water. That's multiplied by 6.01 kilojoules per mole of water. Again, the coefficients in the balanced equation are 1. And the answer is 334 kilojoules. All right, let's consider this process. C6H12O6 is glucose or sugar, and one of those reacts with 6 moles of oxygen to make 6 moles of water and 6 moles of carbon dioxide. And the heat of this reaction is negative 208.802.7 kilojoule. Humans obtain energy from the combustion reaction above, going on a molecule by molecule basis within ourselves. Or rather, well, your biochemist will provide future details in classes you take later. From this equation, you can estimate the amount of CO2 produced if a person uses 2,000 food calories of energy a day. Alright, now to do all this problem, you need a couple of hints. A calorie, English unit of heat I've mentioned before, is exactly 4.184 joules. And here's something else you should be aware of. Food calories are actually kilocalories. So if you look at a can of soda pop and it says it has 150 calories, that's actually 150,000 calories. Alright, you could attempt this before moving on. Convert units. 2,000 kilocalories is 2,000 food calories. And we could convert that to kilojoules by multiplying by 4.184 kilojoules over kilocalories. That gives us 8368 kilojoules. All right. This 8368 kilojoules has to come from the combustion reaction, so this has to be heat released by the combustion reaction. Now be careful in this case. Balanced equation says that there are 6 moles of CO2 involved in the release of negative 2802.7 kilojoules. So you see that I have assembled those into a conversion factor here, 6 moles over negative 2802.7 kilojoules. It's important to include the coefficient for the balanced equation, and this is our first example of a coefficient other than 1 in this presentation. Alright, so this times this converts kilojoules to moles of CO2. You can then multiply that by the molar mass of CO2 over 1 mole of CO2 to convert to grams, and the answer is 131.4 grams of CO2, which is roughly the mass of CO2 you're expected to exhale on a daily basis. All right. This finishes the second presentation for Unit 5.